Today I want to talk about secondary operations. We showed you the lathe and the mill, which does the primary function of our prototype work. But with the secondary operations comes the next level of precision. And the first one I want to talk about is probably the oldest, which is abrasives. In its simplest form, a handful of sand. Let me take that handful of sand and drive it with 120 psi compressed air. I'm going to get a process called sandblasting. Most commonly used probably in the auto body industry to clear off old metal, remove paint, rust, things like that. It's been around so long for them. The old timers will call the resulting surface a gripper surface. That's where they want to start all that priming. But I can put it on a sheet, on a belt, on a disc, and I say it's the oldest because there's documentation of ancient Egyptians using abrasive reeds to polish wood. Now let me take that handful of sand and I'm going to compress it under high pressure. I'm going to make a man-made stone. Now if I take this stone, and I traverse it back and forth in a steel cylinder, the resulting cylinder is going to have an extremely impressive surface finish. Be nice and round and true and very accurate, because the drawback to this operation is time. This is removing fractions of a thousandth per minute, especially the $19 version of a $50,000 machine. This operation is called honing. The $50,000 machine has a mandrel with a groove in it, a single stone, a wedge, and a spring. The part goes over the mandrel, the wedge drives the stone up under a certain amount of pressure. There's a mechanical arm that will traverse the cylinder back and forth on the mandrel. The machine will read the stone pressure. When the stone pressure drops down to a certain amount, the machine will shut down, assuming that the part is to size. Now there's a lot that goes on with that, because as you wear down the part, you also wear down the stone. And that's all sorts of settings that are going to go into this machine to set up the operation. By removing material this slowly, the precision goes through the roof. So now I can hold a bore diameter to that fourth decimal place in inches very easily. Okay? So now we're going to go over there and I'm going to show you what we can do in other configurations of this man-made stone. Okay, I'm going to take the same technology that we used to make that stone. I'm going to put it in a wheel. I'm going to spin that wheel at about 3,000 RPM. And I'm going to traverse it back and forth on a piece of steel. Now, in the milling demo, we said the biggest enemy of any cutting operation is heat. I think you can see pretty obviously I have generating a ton of heat. And the way we combat that is, instead of a stream of air in the plastics, I'm going to use a flood of liquid. This operation is called surface grinding. You will often hear the term hardened and ground. It's primarily used on hardened steel. If you've watched a cutlery infomercial for more than 2 minutes, you heard hardened and ground. If you watched it for about 10, you also heard hardened, ground, and honed to a fine edge, because anytime you just deal with a stone by hand, they consider that honing as well. Again, the drawback is time. This particular operation is dropping down a thousandths in Z, taking a sweep across my part, dropping down again and sweeping back. Again, when you remove material at that slower rate, your precision goes through the roof. So what we get with a surface ground finish is an extremely flat, smooth surface. One of the problems you can have with flat, smooth surfaces, like any of the major support ways on these machines, are flat surfaces riding over each other. So if you lay down a layer of lubrication, travel across it once with smooth edges, you're going to wipe out all the lubrication. But if you look closely at the ways on one of these milling machines, you're going to see a pattern in there. And back when I was a wee lad, it was a guy in the back room with a tool about 3 feet long that would gouge away at these flat, smooth ground surfaces in order to create very shallow voids. And what those voids wound up being was lubrication puddles, so we could maintain the lubrication between the two flat surfaces. Now, let me take this wheel and put it in the configuration of a lathe. I'm going to spin my cylindrical part. I get a cylindrical grinder. With the cylinder that I honed, if I use a smaller wheel, I get an ID grinder. I hook it up to a CNC control, I get an automatic profile grinder. But the neatest one I've ever seen is called a centerless grinder. What we have is a drive wheel, a grinding wheel, a support fence, and that machine will take a 12-foot bar, automatically draw it through, and hold that 12-foot bar to within about 2/10,000ths of an inch in the 12 feet. Again, very high precision, but the cost is time. Which brings me to this. What is this? You might think it's just a piece of wire, but what if I was to tell you this is the most accurate cutting tool in this shop? And if you want to step over to the wire machine, I'll show you what that's all about. Okay guys, how many have done some welding? Okay, what happens when you stay in the same place too long? You blow a hole through it. Well, what if we could control that? So this 10,000th wire is now my welding electrode. I'm going to ground my workpiece. I'm going to generate an electric arc, which we know from welding is hot enough to melt steel. And we're going to control it with a CNC controller. Now in the grinding, I showed you the piece of wire and told you this was the most accurate cutting tool in the shop. And when I say the most accurate cutting tool in the shop, how many decimal places do you see there? 5. Which is telling you that this machine is 10 times more precise than anything else in the shop. Okay, so what it allows us to do is some really neat stuff. All right, this core was done in an older machine, and it took 6 hours to core it out. So the drawback is time. We have 5 decimal place precision, but it takes quite a while. All right. Now, if I can't pass this around, but you would see a 16th radius on this nose. All right. So in order for me to mill this cavity with a 16th radius, it would require a 1/8 end mill about this long. You guys have got just enough machining experience to know that that isn't going to happen. All right. I have a 10,000ths wire. It creates a 12,000ths wide cut, which they refer to as the kerf, for basically a 6,000ths radius. Now, we can go down in wire size, almost all the way down to 4,000ths wire, but that requires diamond guides that go to the tune of about $6,000 per pair. So we're going to stick with 10,000ths wire. So the first thing I'm going to do is I'm going to take the wire and I'm going to constantly cycle it through the cutting area, off my spool, down through the cutting area, and to a waste box in the back. All right? The next thing I want to add is tension. I want the wire to be taut. I don't want it to go waving through however it feels like. All right? The next thing we add is a stream of water. This is to clear out any of the debris in the cut. Have you ever seen a movie with somebody's plasma cutting with a torch? You see sparks flying all over the place. Well, about 2 inches away from the base metal, that is a molten steel re-solidifies almost into a perfect sphere and drops away. If they back the camera up, the person plasma cutting would look like it was standing in a pile of BBs. Well, my pile of BBs looks like a handful of mud. But it's actually the same. It has very, very minute spherical steel balls. Okay, so if they get clogged up in the kerf and they bridge the gap between the wire and the base metal, what happens? It's a short circuit. The current is flowing. Once the current is flowing, the heat goes away, and so does all the cutting. So we're using the water to flush that debris out of the cut. Okay. The other problem we can have is a wire break. If we get too aggressive with our settings, we'll create too much heat, the wire breaks. The machine, when it senses a wire break, will back up through the program all the way back to the beginning of the specific cavity, rethread the wire, at an accelerated move, go back to where it broke and try it again. All right? It will try that as many times as we allow for in the control. Because the last thing we wanted to do is break a wire, spend 2 minutes coming back, rethreading, getting back, going 2,000ths and breaking the wire again and keep doing that. So we wanted to say enough's enough at a certain point. The next problem we have is I don't get that debris out of the kerf, and I keep getting reverse alarms. When it sees a reverse alarm, what it does is it retraces in the program, backing up, hoping that the water can clear the debris and it can start cutting again. It will do this again as many times as we set for in the control before it will alarm out. Now, I said the drawback is time, so it's not uncommon to have one person dealing with a whole bank of these machines. They want to be running 24 hours a day, 7 days a week, 365 a year. Right? So with it that important that they keep running, the newer machines come with a set of contacts in the back that when it gets into that reverse alarm or exceeds the number of wire breaks, we'll dial a phone. I didn't tell BU about that feature because I didn't want a phone call at 3 a.m. from my wire EDM machine. Okay, so the last thing I'm going to add is EDM power. Now, what you're seeing is a skim cut. Normally, the nozzles would be clamped on top and bottom, and the water pressure would be on maximum. This right now is on 1. On 15, the water would come up here, bounce off the roof, and probably clear that table, or hit me in the chest if I was standing in the right place, which I have done 3 times. I call it EDM baptism. Okay. What do you hear? Sounds like a crackle noise, right? Why do you think that is? What happens after the current arcs? It's flowing. When the current flows, the heat goes away, the cut stops. So in order to keep this machine cutting, we are going to constantly restrike a new arc. And we do that with all of these attributes. And the first major one is on time. Right now, this machine has got the current on for 6 milliseconds. The next important one is off time. And that right now is off for 30 milliseconds. If I have too much on time, I break wire. If I don't have enough off time, I get that reverse alarm. So we're looking for the right blend of attributes in here to get our most efficient cutting. In the milling machine, we talked about feed rate, point A to point B, and we told it how fast to go. In the wire EDM, we set our arc attributes, and the machine tells us how fast it's going to go. And it will periodically raise or lower this feed rate in order to maintain the same arc gap between the wire and the base metal. Now, what I'm doing is a very expensive bandsaw at the moment. It's doing all of these cavities. But if you look at this part, you see the top goes in. because this is a 4-axis wire EDM, and with a 4-axis wire EDM, we can do some really neat stuff. All right. What I've done is I've programmed a circle on one face and a star on the other, and it's done by one nozzle runs one program and the other nozzle runs another one. So what you see is your standard XY. When you come over here, we've also added U and V, and U and V is what offsets the nozzles from each other to a maximum angle of 30 degrees. One of the neatest examples I ever saw in a wire EDM piece was a 1-inch thick plate of hardened steel. And if I didn't mention it, the machine cuts hardened steel better than soft steel. I don't know the science behind it. I'm sure the word microstructure is in there somewhere. But anyway, they did a cross-section of the Statue of Liberty on one face, and the wire made a smooth transition to a Christian cross on the other. I've also seen a 2-inch wide block that had numeral 1 on one face, numeral 2 on the other. So, any questions? Yeah.
You mentioned that precision is a big thing for the wire EDM. So what kind of jobs would you recommend doing in here versus another?
Okay, you're going to do, first of all, you're going to do something that you can't conventionally machine. You're going to do something that you need to the 5th decimal place in accuracy. I've done some form tools where you could work taper in to get the taper geometry of the tools. Primarily, you're going to see its best use is a punch and a die. You ever used a punch and a die? Because you've punched a hole in a piece of paper, right? So they have this circle at the top, and it flares out for the die, and the punch has a small land and back tapers. So let me take the bottom nozzle, run a 1-inch square, and I'm going to take the top nozzle and I'll run an 1 10/1000 square. And what I'm going to get is that die shape. All right. Now the machine will actually do a small straight land and then go into the taper. All right. Very simplistic. If you take the slug out and flip it over, you have the punch. So it's hardened steel punches and dies, which would be its major function. To me, the slug isn't the impressive part in this. It's the cavity. And if you think of this like an extrusion die, all right, you know what an extrusion die is? You remember the old Play-Doh Fun Factory? You lift up the lever, you put a wad of Play-Doh in there, you put the window over, you break 3 blood vessels, you get a shape about this long. That was an extrusion process. Okay. Now, all of my little meckies. What's that slot called? It's called a keyway. You take the shaft, you put the corresponding slot in that with a square piece, locks them together. All right. This has got a 10,000th radius in the upper corner. So how am I going to do this? Yeah, I'm more looking for a process. I could do them in here if I could get about $50 a piece for them, but they sell for 20. So naturally we have a better way to do it, and that's over here. You've probably heard the old adage, you can't put a square peg in a round hole. Those people have never been to Epic. So I want to show you round hole. I'm going to take this device, and now my square peg fits in there very easily. This tool is called a broach. Again, we're now dealing with 4th decimal place in accuracy. The keyway, I'm going to start with a pre-existing hole. I put a guide in. Naturally, this is called a keyway broach. And very rapidly, I wind up with my keyway. Okay, 4th decimal place in inches. The drawback no longer is time. because this is now creating parts very rapidly. So what's the drawback? Well, these devices can go for thousands of dollars. Let me start with a very simple shape, a round hole, and I'm going to end up with a fairly complex shape, say a spline shaft. You may not know what a spline shaft is, but you've probably all used one every time you use a drill press. It's the geometry that will allow a pulley to drive the spindle, yet still let you feed the spindle in and out of it. If you look down from the top, it would look like an internal gear on the pulley, and the spline shaft is driven by that. It's very complex geometry to create that, to create a minimal amount of friction. In this operation, let me take this broach, and I'm going to make it about, say, 2 feet long. I'm going to drive it with a hydraulic ram. I'm going to stack up a bunch of parts in front of it and drive it through, and in a matter of seconds, I'm going to go from that simple round hole to an internal spline. Now, the drawback isn't time. I'm getting my 4th decimal place in inches. What is the drawback? Again, that broach is going to be many thousands of dollars. So what do I need to have in order to warrant doing a broaching operation? If I only have 10 of those keyways to do, I'm going to do it in EDM. If I have hundreds to do, now I'm going to invest in a broach. I have to have a high quantity of parts in order to merit the cost that I spend up front for the broach, because it's got to be divided out over all the pieces. All right? Which kind of brings me down to the last thing that I want to talk about. Hopefully at this point you're dealing with classes that are talking about fits and tolerances. Hopefully, because it's getting late. But anyway, it's very difficult for us to make tolerances real to you. It's just kind of a concept. Unless you've spent some serious time down here, plus or minus 5 thousandths to you doesn't mean much. What I can tell you is a plus or minus 5 tolerance. The milling machine and the lathe that we showed you is gonna maintain that all day long without even breathing heavy. It's when you get down into the splitting that last thousandths of an inch that you wind up in these secondary operations. All right? The problem you run into when you don't have much experience designing a part is to fight the urge to say, I'm going to put plus or minus 1/1000 tolerance on every dimension of my part, and I'm going to get an extremely accurate part. And you're right. It's going to be incredibly accurate. Once you design something, most companies don't have the manufacturing facility right there. You're going to send it out for quote. Your boss says, I need to get this part for about 50 bucks. You send it out for quote, it comes back at 150. What happened? Don't worry, there's plenty of time in the unemployment line for you to figure that out. But what I can tell you is, you've toleranced this thing in so many different ways that it's forced somebody like me into a bunch of these secondary operations. Because along with the next level of precision comes the next level of cost. So what it comes down to is, there are times you are going to need that 4th decimal place tolerances in inches. You're going to press a bearing into an aluminum housing. You need the 4th decimal place, and not very many of them. You're willing to pay for that. It's what happens on the rest of the part that you can create lower cost based on tolerancing some of the lesser important dimensions and loosening them up. It's a tough thing to learn, and it's going to have to come with some experience. So good luck. Take care.